Good morning. Now I am going to explain you about splitting of octahedral complexes according to crystal field theory. Here I represented an octahedral complex where the center position will be the metal atom and the metal atom with 6 coordination number. That means it will be connected to 6 ligands at the corners of this octahedron. And here I just listed few of the octahedral complexes with weak ligands and with even strong ligands, and all these how the d orbitals of the metal atom will be repelled, will be experiencing the repulsion by the ligands, is what explained by the crystal field theory. And before going to discuss about the splitting of an octahedral, just take a look about the structures of d orbitals, 5 d orbitals, how they orient, whether they orient along the axis or in between the axis. We just take a look of that. And this is what here I represented 5 d orbitals, and this is dxy. I considered this as x-axis and this as y-axis, and dxy orbitals are non-axial orbitals where they are lying in between x and y-axis. Even dxz is also in the same way. They'll be oriented in between x and z, and dyz is also a non-axial orbital where their lobes are arranged in between the y and z. Whereas this dx square y square and dz square, the orientation is along the axis dx square y square. The probability of finding an electron is maximum along the x and y axis. Whereas dz square, it is in the donut shape where the maximum probability will be along the x-axis and they'll be around the center, which is in the form of a donut, and these two are considered as non-axial orbitals, which are represented as Ag, and whereas these three orbitals dxy, dxz, dyz are considered as non-axial d orbitals, which are represented as T2g orbitals. And then octahedral is considered, how the octahedron is experiencing, how the metal atom is experiencing the repulsion, whether they are experiencing repulsion, these three are experiencing more repulsion or these two are experiencing more repulsion. Just we'll discuss now. And generally Eg orbitals are called as double degenerated, and T2g orbitals are considered as triply degenerated. And earlier we have seen the structure of an octahedral complex where 6 ligands are along the axis. They are situated along the axis. It can be x-axis, y-axis and z-axis. So obviously the orbitals which are along the axis, that means axial orbitals, will experience more repulsion than non-axial orbitals. And this is what splitting I represented. And generally an hypothetical condition is considered. Initially, this is what the degenerated state of a metal atom when it is not under the influence of ligand, and when ligands are approaching in a same direction, in all the directions, if the ligands are approaching with the same influence, then this is what isotropic field we consider. And this is I'm saying you, this is an hypothetical degenerated state, and all the d orbitals will be excited to a higher level and but still remain degenerated. But actually this won't happen when ligands are not approaching in the same direction and with the same influence. So obviously when the ligands are approaching along the axis, these Eg orbitals, which are called doubly degenerated orbitals, will be repelled more, and whose energy will be raised by 0.6 delta, or it can be given as plus 3 by 5 delta O, whereas the T2g orbitals, which are non-axial orbitals, are not along the ligand approach. So obviously they are not repelling by the ligands, and the energy of these three orbitals will be reduced by 0.4 delta O, or it can also be equal to minus 2 by 5 delta O. And the difference between the energy gap between the T2G and EG will be equal to 10 dq, or it can be represented as delta O. And if you consider the T2G orbitals will have low energy than EG orbitals. When electron filling is considered, electrons will be first filled into the T2G orbitals and then into the EG. Whether the electron is paired within the T2G or they'll be jumping into the EG, that depends on the ligand, the approaching ligand, whether it is strong field or weak field. Based on that, the pairing of electrons will be considered. Obviously, the energy, the crystal field splitting energy or crystal field stabilization energy for a complex will vary from other compound based on the ligand approach. I just want to differentiate how the strong field and weak field ligands will be there. And if you consider the strong field ligand, the gap between T2G and EG will be more, whereas weak field ligands, the gap between EG and T2G is very less. So obviously electron can jump into the EG in case of weak field, whereas in case of strong field, the electron will be paired up first into the T2G, means first 6 electrons are filled into the T2G and the 7th electron will enter into the EG. Whereas in case of D1 to D3, the electrons will be filled in T2G, where D4 system, the 4th electron will enter into this EG. That's what I represented in this tabular form, where even the crystal field stabilization energies are also varies. If you consider the D1 system, D1 to D3 system, there is no more question that only T2G orbitals will be filled. The single electron will be entered into the suborbitals of T2G, whereas D4, this is what the table I represented in case of a strong field ligand, where the 4th electron is entering or pairing up into the T2G orbitals. And in the same way, after the 6 electrons are paired up, then the 7th electron is entering into this EG orbitals, and then obviously there's 8th electron into another EG, and then pairing will start. And take a look of stabilization energy. So initially 1 electron is there, so obviously its energy is 0. minus 0.4 delta O, and this is 2 electrons means minus 0.8 delta O, and I represented here even the lone pair of electrons, and the energies are varying according to the pairing or number of electrons. This is what I represented in this table. Even in case of weak field ligand, this 4th electron will not enter into this EG, T2G will be entered into this EG, and according to that the crystal field stabilization energy is also varying. The crystal field stabilization energy is given by a formula that 0. minus 0.4 into T2G electron plus 0.6 into number of electrons in EG into delta O. According to that, we can calculate the stabilization energy. Thank you.